let's start this up again. Okay, so does this all look familiar to everybody? Linear equations. They have this form. You need to know the integrating factor as well as the new problem that you have to solve. It's pretty easy to solve for y from here. We just simply have to integrate both sides and then divide by capital I, right? Okay, so the next one is the Bernoulli differential equation. And for a Bernoulli equation, we have y prime plus p of x y equals q of x times y to the n, right? So this is the difference. It's not a big difference, but it is a little different than a linear equation because there's a y to the n on that, okay? Now, when you have a Bernoulli equation, what you have to do, going back to September, is we have to change the variables, right? And the change of variables, you need to know this. U equals y to the 1 minus n. So this is the way we will usually write this one down, right? U equals y to the 1 minus n. And when we use that change of variables, we get a new differential equation. So you don't have to be able to derive all of this, but I just want you to see it here. U prime plus 1 minus x p of x u equals, careful there, Travis.
Yep.
That's a very, you might want to pick a different spot. Yeah, thank you. Equals 1 minus n q of x. So this is what the Bernoulli equation becomes after you change variables. Okay? So make sure that you know the formula there for the change of variables and the new equation. Okay? So there are a lot of parts of the class where there are not very many formulas, but this is one section where there are. There's a lot of boxes on the board already. So this is a Bernoulli equation. And then the last one that you want to maybe go back from chapter 1 to review are the homogeneous differential equations, which are the ones where you have y prime equals f of x and y, and then you have to replace, if you replace every single x and every single y with a t next to it. So if you attach a t next to every x and you attach a t next to every y, the t's all cancel right back out again, right? So if you have this situation where the t's just cancel right back out, then this is homogeneous, and in this case, the change of variables that you need to use is y equals xv, okay? And along with that, you're going to have, of course, you're going to need to plug in for the derivative of y, which is y prime, which is xv prime plus v. So there is the, the change of variables for the homogeneous equations. Okay? So this is just like a crash course on chapter 1. The 4 main types of differential equations: separable, which there really isn't any formula for, linear, Bernoulli, and homogeneous. Okay, so far so good? Let's go back to the original problem that we're solving here now, and let's dive into it. Y prime minus 3 over 2xy equals 6y to 1/3 x squared ln of x. So that is Bernoulli, as we said. What is the n value in the Bernoulli equation? It's just the power of y on the right side of the equation, which is 1/3. So n is 1/3. So we're going to do a change of variables, which is going to be u equals y to the 1 minus n. So that would be y to the 1 minus 1/3, or in other words, y to the 2/3. So u equals y to the 2/3. And you don't really need to use that yet. I just like to write it down, but then we're mainly going to go to this box right here. Okay? So what we're going to have is u prime plus 1 minus n. Make sure you get this number correct. It's 2/3, right? 1 minus n is 2/3. If you get that wrong, the whole problem is going to go to hell in the handbasket, right? So you got to get the 2/3 in there. And then we have the p of x. P of x is just whatever the coefficient of the y was right here. Be sure to include the minus when you're subtracting. That's part of the p of x. So negative 3 over 2x, and then that's times u. equals, and then 1 minus 1/3 is 2/3 of q of x, and q of x is everything on the right side except for this power of y, right? So that would be a 6 x squared ln of x, just like that. Okay. Great, so this becomes, now this new differential equation is always linear, right? So it becomes, a Bernoulli equation will become linear after you do this change of variables.
So, quick question, the n minus 1?
1 minus n, 1 minus n.
Okay.
Very, very, a lot of people mess that up. It's got to be a 1 minus n.
Okay.
So the n is the power right here, which is 1/3.
Right.
So 1 minus that is what you're putting.
Yeah, I wrote it right, but said it wrong.
Okay, no worries.
So the 1 minus n is 1, for this problem is 1 minus 1/3. So our 1 minus n equals 2/3
Yes.
for this problem. Okay,
Yes.
I see. Thank you.
Absolutely right.
Okay.
More people than you might think actually get this mixed up with n minus 1 and get it mixed up with what n itself is. So the n itself is 1/3, but it's actually 1 minus n that you're plugging into this change of variables here. Okay, so this is our equation. I could simplify it a little bit. Let me come up here. We have u prime, and then notice that all these fractions are going to just cancel away. We're going to get minus 1 over x times u. 2/3 of 6 is just 4, so we get 4x squared ln of x. So there is our new linear equation that we have to work on. Okay, so we can now work out the integrating factor here. So the integrating factor is e to the integral of p of x, but guys be careful, the p of x is from this equation, which is negative 1 over x dx. Okay, and then this becomes e to the negative ln of x. Technically, there would be a plus c on the end of that, but I'm not going to write that down because you don't need to, right? You can always choose c to just be 0 for these kind of problems. So you just choose c to be 0. And so then this becomes what? How does this simplify? E to the negative ln of x?
X to the negative 1.
X to the negative 1, in other words, 1 over x, exactly. So there's my integrating factor. Just let me know if there's any questions as we go along. Normally at these review sessions I say, well, I'm not in a hurry. For those of you who just came in, we have to stop at 6:45 tonight. They are going to turn the power off on the building. I didn't get a warning about this until yesterday. So we're going to do as much as we can in an hour and 45 minutes, and then hopefully be able to use our cell phone light to get us out of the building without tripping. Yeah?
We don't need an absolute symbol for the x.
Oh, I was going to mention that. So technically this is the ln of the absolute value of x. However, x has to be positive already in the very first place. Otherwise this question doesn't even make sense. So we can kind of assume that x is greater than 0. But that's a great point. Absolutely right. Okay, so now I'm going to write down my product rule derivative. 1 over x, which is I, times my unknown function, which at the moment is u. We have the derivative of that product equal to q of x. So here's q of x right here. It's on the right-hand side of this part of the problem, but we have to multiply that by the 1 over x, so it just becomes 4x ln of x. Okay? All right, great. And so then the next step is going to be to integrate both sides. So on the left, of course, I just get 1 over x times u. On the right, I can take out a factor of 4, and then I have to integrate x ln x. Now that one is in your table of integrals that you'll have on the test. So I'm just going to tell you what it is right now, because it'll be something that you have. It's 1/2 of x squared ln x minus 1/4 x squared, and then there is a plus c on that, and in this case you do need to include the plus c. So this is coming from the table, the integral table. Okay, so that would be that. We could also multiply the 4 through if we wanted to. You don't have to, but I will. If I am going to multiply through by 4, please, if you have like 4c, don't call it c again, call it like c1. It's a different constant, because if we FOIL the 4 through, or if we distribute the 4 through the whole equation, 4 times c is not c, right? 4 times c is some other number, which I'm going to call c1. Okay, great. So now I can figure out what u is. Just come over here to do that. It's nice to do these Bernoulli examples because they also review linear equations kind of at the same time, which I think is useful to do. So let's see. Okay, so thus what we have is u equals, so I have to multiply through by x, right? I just have to throw an x through this whole thing. So it would be x times the quantity 2x squared ln x minus x squared plus c1. That's what u is. And then, of course, that's not my final answer because I don't want to know what u is, I want to know what y is. So I have to come back here and remember that u is y to the 2/3. So just reminding ourselves from the beginning that u was just y to the 2/3. Okay? So if I want to get y by itself here, what would I need to do? I know what y to the 2/3 is, so how do I figure out what y itself is? Exactly, take both sides raised to the 3/2, right? If you raise this to the 3/2, right, and then you also raise this to the 3/2, it should be still valid. And remember that here with this sort of two-step exponentiation, you multiply those fractions. So 2/3 times 3/2 is just 1. So y becomes x times 2x squared ln x minus x squared plus c. All of that, all raised to the 3/2 power. Oh, and that should be c1, sorry. I changed it to c1 there. Okay, so there's the answer. This would be the general solution, right, to the differential equation. Okay. Does that make some sense so far? You doing all right? Okay, great. So in chapter 1, you need to be on top of those separable, linear, Bernoulli, and homogeneous differential equations. And you go back to the first midterm. I posted blank copies of the midterms on the website, so you guys can print them out again and try them from scratch. Since this is much older material that we didn't really come back to that often, it's definitely going to be good to review it. We had a couple of applications in chapter 1. We had the Newton's law of cooling, and we had the mixing problems. Diane?
In the exam or the final,
Yeah.
how would you word the question? Just like that?
Just like that?
Okay.
I would just say solve the equation, yeah. For those of you in Math 207, there's a couple of you here, we also studied orthogonal trajectories and Euler's method in chapter 1. So you will want to, George and Coco, make sure you look at that as well. But yeah, the main applications are the Newton's law of cooling as well. Remember the Newton's law of cooling? Maybe I should write it down just to get it back in mind here. This is the one that says that the rate of change of the temperature of an object with respect to time is negatively proportional to the difference between the temperature of the object and the temperature of the medium. Right, so this is the Newton's law of cooling. Remember that this is a separable differential equation. And if I ask you what is I've done this before on a final. I remember one time I said, what is Newton's law of cooling? This is what you want to write down. Some people think that I'm looking for the answer. So of course we can solve this thing by separating it. Separate the big T from the little t. Right? We actually did this in class way back, I think pretty much the second day of the semester. You can actually solve it by separating it and then integrating, right? The left side gives you an ln of t minus tm. The right side gives you a negative kt plus c. And if you just exponentiate and then remove the absolute value bars and then move the t sub m over, you actually have a nice formula that some of you maybe remember, that the temperature of the object is equal to the temperature of the medium plus what ends up being C2 times e to the negative kt. Okay, but what you have here is not a differential equation. Like, I don't have any derivatives there. This is the result of solving Newton's law of cooling differential equation, which is this one right here. But this is the one you really want to make sure you can remember, and then this is the derivation of the solution, or at least I skipped a few steps here, but you'll see the full details in your notes. And then from there I can ask a question where you would use this to solve it, but most likely I would want to have you do this derivation because this is the 250b part. Plugging numbers into this equation is a high school problem, right? Actually, you probably need a calculator anyway to do that. So it's more important probably to know this. As far as the mixing problems goes, I think I would give you that equation. It's got so many different variables in it, it's a little hard to remember. There's a differential equation for the mixing problems, which is basically something along these lines. You may kind of remember this one as well. This is for the mixing problems. This one is linear. But if I was going to ask one of those, I would provide you with that differential equation. This one here, just because it's got 1, 2, 3, 4, 5, 6 different variables in it, and it's not really necessary to memorize that. So anyway, so that's chapter 1 in a nutshell. Any questions about any of that? So Bernoulli equations always become linear. Homogeneous equations, when you apply the change of variables y equals xv, always become what? Separable, right, separable. So it's good to remember that. So every Bernoulli equation is going to turn into a linear one, like on the example we did a minute ago, and then every homogeneous equation is going to become separable. I don't think I'll do a homogeneous example right now. If people don't really need me to, I'll save that for your practice, and I can always come back to it later. But I want to get a variety of things looked at here. So let me give you a few more examples. Or I'm going to change topics again. Okay. Sorry, this is going to be kind of a potpourri of topics. This next one is not from the review session packet. It's just one that I thought was kind of a nice question. So here it is. Let S be the set x comma y comma z such that the distance from x, y, z to the point 0, -3, 4 is 5. So I actually am expressing it in words here. Pretty much what it is. And then my question here is going to be, is S a subspace of R3? So we're very quickly jumping into the middle part of the semester where we're talking about subspaces. Remind me again, for subspaces, what's the requirement that we have to verify if it is a subspace? Closure under addition and scalar multiplication, right? So we have to think about closure under addition and scalar multiplication. But before we just dive into trying to check those things, we might want to have a good idea about whether the answer here is yes or no. Because if the answer is no, then starting to plunge into showing that it is closed under addition and scalar multiplication is bound to fail, right? So I would rather get an idea about a yes or no ahead of time. So what's something we can do first and foremost that would be you know, possibly useful to us in deciding whether it's a subspace or not?
A zero vector.
The zero vector check, exactly. So the zero vector check, so I don't know whether this is a yes or no yet, but I'm going to check the zero vector. So if I think about the zero vector in R3 is 0, 0, 0. The question is it in S? Is the distance from 0, 0, 0 to 0, negative 3, 4, is that distance equal to 5? How do you find the distance between 2 points? Let's see. So the distance between 0, 0, 0 and 0, negative 3, 4 is
0 squared plus negative 3, or no, the difference. X2 minus x1 squared, y2 minus y1 squared, and z2 minus z1 squared.
That's right. You take the differences of the components and you square them up, and then you take the square root, right? I mean, if I give you 2 points, you know, x1, y1, z1, and I know we haven't done this example before, so, you know, but this is the distance between these points, just the square root of the differences of the coordinates squared. Does this add up to 5?
Yes.
Square root of 0 plus 9 plus 16, that's the square root of 25, that is equal to 5, which is a yes. So is the zero vector in the set?
Yes.
Yes, it is. Okay, does that mean that it is a subspace of R3?
No.
It does not. If the zero vector was not in the set, then we could definitively just say no, right? We could just right off the top say, nope, it's not a subspace because there's no zero vector there. But if the zero vector is in the set, then we have to investigate further. Okay. So I'm wondering, you know, we still don't know whether this is a yes or a no. I'm wondering if anybody has any thoughts or any ideas here. We're working in R3, so it's something that we can visualize potentially. If you could describe what S is as a shape, is it a point? Is it a plane? Is it something else? Diane?
It's a plane only in the YZ.
Okay, so I'm gonna actually draw so this thing I drew right here is the whole R3, right? The whole R3 is right there. And we're talking about which points does S consist of. Well, obviously I have 0, 0, 0. We already checked that one. So 0, 0, 0, that's part of the set S. So what other points are in S? Well, it's supposed to be the points that are a distance of 5 away from 0, negative 3, 4. I'm just going to plot that point somewhere random. I'm not a very good artist, so I'm just going to plot that point maybe right here. I don't even know exactly where it belongs, but it's like 4 units below the xy plane, and it's got a y component of negative 3, so I probably should have drawn it over there. But anyway, you kind of get the idea, right? Actually, it should be, this point should be in the yz plane, right? The x coordinate is 0, and in the yz plane, we just need to go 1, 2, negative 3 in the y direction, and 1, 2, 3, 4 units in the z direction. Okay, so I'll try and do a better job of drawing my point. That's about where my point is. And what we're doing is we're talking about all points that are 5 units away from that red dot, and the origin is one of them. So what would this collection of points look like physically, Brandon?
A sphere?
It is a sphere. It is absolutely a sphere. All of the points that are the same distance from that red dot forms a sphere, right? It's a sphere of radius 5 that is centered on the red dot. If you are anywhere on that sphere, you are going to be 5 units away from that red dot. It's a sphere. Do you see that? Does it make sense? We've not done one of these before. I'm trying to throw something a little different just to give you an idea. Now, is that going to be a subspace? I mean, when you think about subspaces, you should be thinking about linear spaces, lines, planes, right? Those are the kind of things that are linear. A sphere is about as curved as it could get. It's as far from being linear as possible. So I'm going to take a wild guess that the answer here is no. Probably not going to work. And if the answer is no, then what I really need to do is come up with like some failure of the closure of addition or scalar multiplication, something like that, right? That's kind of what I would be hoping to find. Okay. Well, it's not going to be that hard to figure out what we could do, so we need to either take 2 points that are on the sphere and then add them together and have the result off of the sphere, or we need to take 1 point that's on the sphere and stretch it by a scalar and have it fall off the sphere, right? And I can kind of see a possibility here. I mean, this z-axis, there's lots of ways to think about it, but do you see that this z-axis is going to penetrate the sphere? There's a point up here somewhere, 0, 0, something. Well, maybe it looks to me like, I'm not exactly sure what that point is. So it's 0, 0, something. We could figure out, I'll call it A, but we could figure out what's the distance between, between these points here. But the point is, if you take that point 0, 0, whatever, and you double it, in other words, you go twice as far up the z-axis, you're not on the sphere anymore, right? So what we can say here is, I'm just going to use this as my example. Closure under scalar multiplication fails. So when something fails like this, whether it's matrices or whether it's polynomials or whether it's something else, right? In this case, it's just points in R3. We can justify it by just giving an example. So consider the point 0, 0, A. I don't even know what A is, but this is an element of S on the z-axis. Okay? Then if we take, so when we're disproving the closure, let's say we double this point, 0, 0A times 2, what that's going to give you is a new point, which is the point 0, 0, 2A. And you're just doubling the coordinates of the point. So you just multiply through by 2 here. Well, you get something that is not in S anymore. Okay, because and you can see that geometrically because it's farther up the z-axis than this point was, right? So thus, S is not a subspace. Right? So we don't have a subspace here. Does this make some sense? You know what would have been easier? I could have done this a little bit more easily. I could have picked the point that's directly above the red dot here, which would be the point 0, -3, 9. That's definitely 5 units above. That's exactly 5 units above the center of the sphere. So just take the point 0, -3, 9. Well, if you double that point, you get the point 0, -6, 18, which is going to be way much further away from that red dot than 5 units. Okay, so you just have to pick one specific illustration that shows the failure of the scalar multiplication, and that would do it. Okay? So I'm really trying to go back and review like some of the earlier stuff here with this. Let's do another one of those to practice a little more. Is everybody good with this example? Okay. Guys, if it's not a point and not a line and not a plane, and it's in R3, it's not a subspace. In fact, if it's not a point, it's the origin. If it's not a line through the origin, if it's not a plane through the origin, it's not a subspace of R3. Because you have to have the zero vector. right? So, okay, let's do another example. Let's do something, let's do something here. Okay, so here's another example. This is also not off of the review session questions. Let's take this one. Let's let S be equal to the set of P of X in P3 of R such that P of -1 is 0 and P prime of 1 is 0. And what I'm going to ask is S a subspace of P3 of R? Just try this one for a minute. Okay, actually I'm going to give myself a little more room. Is the zero vector in there? Okay, well, first of all, what is the zero vector here? We're working in a world of polynomials now this time. So the zero vector is just the zero function. It's actually a graph. The zero vector, if I just think of it as a picture, is literally just that. Sorry, it's supposed to be a straight line. It's just the function that if you graphed it would just cover the x-axis, right? This is your zero vector. It's a picture of it. And what I'm asking you is, if you plug in -1 into this function, do you get 0? Well, you definitely do. And is the slope of this function when I plug in 1, is this slope equal to 0? And it definitely is, right? So the zero vector check, again, passes. We don't get a fast rejection of this example, right? This one, we're going to have to work a little harder. Okay, so the next thing to think about is, all right, despite the fact that the zero vector is in the set, right, so in other words, 0 is in S, despite the fact that that's true, the question is, do we think it's closed under addition and scalar multiplication? So if I take two polynomials, both of which go through this point, and I add them together, do I think that the result will still go through that point? So, you have -1, 0 on two different graphs, P of X and Q of X, let's say. Right? My intuition tells me that if I take -1, 0, right, and I have another function that also goes through -1, like if I have one graph here, right, and I have another graph here, right, and I visually add them together, my intuition tells me that my picture is going to be pinched right here at this point. Should work, right? And if I have two graphs that are both flat right as they pass through an x value of 1, so I don't know what the whole picture looks like, but let's say I know at least that they are flat right there and flat right there. When I add those together visually, will the result be flat at that spot? Take two things that have a derivative of 0 and you add them together, does the result still have a derivative of 0? That seems reasonable. So, it's likely both of these conditions seem to work. Now, if I changed this to like a 1, and now I'm saying, okay, so I have a function that has a slope of 1 at this point, and then take another function that has a slope of 1 at that point, the slope of the sum of those functions would now be 2, because 1 plus 1 is 2. Right? You've probably got this idea that you almost always have to have a 0 there. In these conditions, having that 0 is really required. Okay, let's try and prove this. Let's try and prove that this thing is closed under addition. so how do we start that off?
Sorry.
Somebody else want to take the next word or the next notation? We need names for our vectors, right? I have to take two vectors. P of x, great, let P of x, and we need another one. What would be another good name?
Q of X.
Oh, I'm so glad you said that. A lot of people say, I see people say P of y right here, and guys, P of x, P of y is the same thing, right? You're just changing your dummy variable of the function. So you don't want to do that. So make sure you're changing the P and the Q, not the x, to something else. So it's P of x and Q of x, B in S, right? That's what we want to say. Now, what does this mean? This means, let's just literally write the text for it here. This means that, okay, if P of x is in S, it means it satisfies that condition. So P of negative 1 is 0, and also P prime of 1 is 0, and Q of negative 1 is 0, and Q prime of 1 is 0. All four of those things are true. Okay, so all four of those things are true. Now, what vector do we want to look at right now? What's the vector that's in our spotlight? Say again? Not the 0. We're done with that one. We're done with the 0 vector. Anybody? What are we checking right now?
P plus Q.
P plus Q, closure under addition. Exactly. So we're going to check closure under addition. So that's exactly what I'm going to look at. So consider, P plus Q of x, right? We have a new function, which is P plus Q of x, okay? What I want to know about that vector is, does it belong to S? In other words, when I plug in negative 1, do I get 0? And when I plug in 1 into the derivative, do I get 0? Let's check it. We have to write out this verification, right? So what are we going to say here? We're going to say if I take P plus Q of negative 1, well, you're just simply adding two functions here. This is literally P of negative 1 plus Q of negative 1, which is 0 plus 0, which adds up to 0. Right? And so this is good, but we also have the second condition, which is P plus Q prime of 1, right? We're going to plug in 1 into this thing. So this is going to be P prime of 1 plus Q prime of 1 equals, okay, so again, P prime of 1 is 0, and Q prime of 1 is 0, so that's also 0 plus 0 equals 0 in both cases. So this is I'm checking both of these conditions here that are required for the elements of S, right? Okay, so thus, don't forget this next line. This is really important, which is that P of x plus Q of x is an element of S. Right? Put a check mark there. So when we add them together, the result is still in S. Okay, does that make sense? This is closure under addition. What else do we need to check? Scalar multiplication, exactly. So closure under scalar multiplication. How do you want me to start writing that one down? Let P of x be as above, great. And what else? K is a constant, I'll just call it a real number. So K is an element of the real number set. So yeah, so we could just write it exactly like that. Great. Sorry, George, I just realized you're here and I didn't give you back your homework edit, I think. There you go. Okay, so we're going to look at K times P of x. So we have two things to check here, right? We have to check. Okay, so then we're going to check if we take K times P and plug in negative 1 into it. Okay, again, I'm just coming back to check these two things, right? What do I get right here? K times P of negative 1 is what? K times P of negative 1, and that equals? K times 0, and that equals? 0. Great. And we also have to calculate K times P prime of 1. And what does that equal to?
K times P prime of 1.
K times P prime of 1. And that is equal to?
K times 0.
K times 0, which again is 0. So there you go. Right. So K times P of X is an element of S. Just take a breath and just be sure to always write this down at the end. If you're circling yes over here, yes it is a subspace, then that means you're going to end every proof with, you know, P plus Q is in S and K times P is in S, right? When you add the vectors together. Okay? And this problem we're working with polynomials, so writing things like P of X and Q of X makes a lot of sense. And yeah, so that takes care of that. Now I'm going to ask you a follow-up question now. By the way, before I ask the follow-up question, do you notice that in this whole entire problem, I never had to write out ax cubed plus bx squared plus cx plus d? Never had to do it. And if I had done that, this would be a lot messier, because you'd be writing out all those terms for the polynomials every time. Why didn't I have to write out ax cubed plus bx squared plus cx plus d? It's because of the way the set S was given to me. Right here, you notice there's never a mention about the coefficients, right? It just literally gives you this and this. So you're able to push this whole proof through just in the sort of surface level of P of X and Q of X without getting your hands on the individual terms. Okay. I mean, I could change this problem very easily. I could put something else up here that says something like, oh, I don't know, so this could, I could write this as ax cubed plus bx squared plus cx plus d, and then over here I could give you a condition like a is equal to b plus c plus d, or I could give you something like that. And now your whole entire write-up is going to be totally different. So it depends on sort of the way in which the set is described to you. Okay, so now I want to do a follow-up question here. We have a subspace, and so once we have a subspace, there's a natural follow-up question, which is to ask you, and be sure to read the questions carefully, guys. So I might say, is it a subspace, yes or no? And then there could be a follow-up, which is find a basis. Follow-up, find a basis for S. And notice, I'm not asking for a basis of P3 of R. A lot of people on a problem like this, they just write this down. It's way too lazy. This is not going to be right. This is the basis for the huge P3 of R that we have to begin with. We're looking at a smaller set here, so we're going to have to be a bit more careful than that. Okay. Does anybody have an idea how we're going to do this? Can't remember if I did one of these back in October when we were kind of learning this stuff. I may not have, but that's okay. This is a good time to review it. This is actually where you need to write out the ax cubed, bx squared, cx, and d. Right? So what we're going to do here is we're going to, for this one, we're going to write P of x. We just want to get the, basically what do I need to get a basis? I need the form of P of x. I need to get the form of my polynomial, and then I'm going to just bust out the variables and get my basis. Right? We've done that so many times, right? So we're going to try to get the form of this P of x. Now, at first, you might think that this is the form. Right? You might think that this is the form, but this is actually not incorporating our assumptions here. Right? This would be the form of any cubic polynomial. But we have constraints that we need to make sure to incorporate. We know that if we plug -1 in for x, we're supposed to get 0. and if we put 1 into the derivative of this function, we're supposed to get 0. So those requirements, these conditions, are going to tell me things about A, B, C, and D. So let's just see what happens, okay? So if I plug in -1 in for x, let's see, -1 cubed is -1, so negative A, and then plus B, and minus C, and plus D, that has to equal 0. I'm going to put a box around that. That's when I plug in -1 into the polynomial. And then I also need to figure out the derivative of this polynomial, so I'm just going to use the power rule to take the derivative. I'm going to get 3ax squared plus 2bx plus c, and now I'm going to plug in 1 into that. So I'm going to plug in 1 for x here, and I'm going to get 3a plus 2b plus c, and of course that's also supposed to be equal to 0. So we have, in those two boxes there, we have the conditions on the coefficients that comes from the original set S, right? So that's what we're going to be working with. Anybody have an idea what I would do next with those two equations? It's absolutely right. Put it in a matrix. Like, it's so often just the go-to thing to do. Now, when you're putting these are a system of equations. I know that I've been harping a lot about putting vectors into the columns of a matrix, but let's be careful with that. That's when you're testing vectors for linear independence, right? Or testing whether they span a set. When I just want to formulate a system of equations, there's no need to do that. You can just lay these equations with the coefficients right across the rows of the matrix, right? We have, 4 variables that are associated with those first 4 columns. And the second row is going to be 3, 2, 1, 0, and 0. This is your augmented matrix for that system. Okay, so this is literally, something from chapter 2. Taking these 2 box equations and putting them into the rows of this matrix here, okay? Now, I'm going to do an ERO on this. I know I've been a little bit lax with EROs in the last few weeks of the semester, but we've got to be careful still to do it correctly. Because we get mistakes, then it's really going to throw things off. I'm going to multiply the first row by 3 and add it to the second row. So multiply the first row by 3, add it to the second row. I think this is what I should be ending up with. Okay? Always a good idea to circle the pivots. I know I didn't make those pivots equal to 1, but that's okay. Okay? So this is what we would have. And so which of my variables are the free variables? C and D, right? So I'm going to let C equal R, and I'm going to let D equal T. Do something like that. And then I have to figure out what A and B are in terms of those free variables. So let's start with the B variable. If you need to, and I would actually recommend that this is a very good idea, take the second row and rewrite it again as an equation. What does it say? 5b minus 2c plus 3d equals 0. And if you solve that for b, if you just solve that one for b right now, you're going to get 2/5 of c minus 3/5 of d. Okay? And because c and d have been relabeled with r and t, this becomes 2/5 of r minus 3/5 of t. That would be the b equation. So we put that for b. How do we figure out what a is? Same thing, but with the top equation. Exactly, the one on top, right? So this equation on the top is what? Negative a plus b minus c plus d equals 0. I can solve that for a, right? If I do that, a is going to equal b minus c plus d. I can just move the negative a to the other side of the equal sign and solve for a. And now what I have to do is just reduce B, C, and D in terms of R and T. So the B was 2/5 of R minus 3/5 of T. And then the C was just R and the D was just T. So 2/5 of R minus 3/5 of T, that's the B, minus C plus D. I can simplify this. This is going to be negative 3/5 of R plus 2/5 of T. Okay? So I get negative 3/5 of R plus 2/5 of T. Right? That's the A variable. So far, so good? Okay, so we're coming up with a basis for S. I'm erasing what S is, but you guys have it. So tell me how you like this. I'm going to take those expressions there. I'm going to bust out the R, negative 3/5, 2/5, 1, and 0. And then I'm going to bust out the T, and I'm going to get 2/5, negative 3/5, 0, and 1. And this would be my basis. Is everybody happy with that? Because you shouldn't be. What have I done wrong here?
Yeah.
Checking for linear independence is a good point. Now there's only two vectors here and they're not multiples of each other. You can pretty easily see that. So these are Li, but there's a bigger issue. And a lot of people made this mistake on the midterm a week ago. So it's a good time to get it cleared up here. Does everybody see what the problem is?
What was that in P of 3 of R?
We're talking about P3 of R, guys. We're talking about cubic polynomials. And all of a sudden, these don't look like polynomials at all, right? That's exactly right. What we need to do to get it right, instead of doing that, okay, so really catch yourself on this, because this is something I will take off for. You have to replace the A, B, C, and D into the polynomial here, and then bust the free variables out of the polynomial. So that's exactly right. So P of X, if I'm going to get it in terms of polynomials, I would have, negative, okay, I can't quite read that, 3/5 of R, negative 3/5 R plus 2/5 of T, that's times X cubed. And then the BX squared, that's 2/5 of R minus 3/5 of T times X squared. Whoops, that's T. Okay, and then plus R times X, and then plus T. So you have to just write the polynomial with the A, B, and C, and D written into it. And now, so guys, if I had just said, give me a basis for all polynomials of this form, right, once you have the form written down, all you have left to do is to bust out the variables. Do you guys remember there was a homework problem where it said the 4 entries of the matrix, it was a 2x2 matrix, and it said the 4 entries of the matrix add up to 0. Right? So the key part of that problem was to say, look, all right, I've got to fill in my matrix here. I can choose 3 of them however I like, and then the last entry has to cancel out the other 3. This was the key step, was writing the form of the vectors. This was a matrix example. Right now we're doing a polynomial example, but in any kind of problem, whether it's matrices or polynomials or traditional vectors, we need the form of our vectors from our space, and we can then bust out our variables. So here I have, I'm going to bust out the R. I'm going to see what I'm left with. I have a negative 3/5 right here with the X cubed on it. And then on the next term, I have plus 2/5. I have the R and then X squared. And then the next term is Rx, so I would just have the X left over. Okay, and then plus T is my other variable. Let me bust it out as well. When I bust out the T, I have 2/5 of X cubed, right? Minus, make sure that if you have a question how I'm doing this, be sure to let me know. Minus 3/5 of X squared and then plus 1. So my basis is just those two polynomials that are in the brackets, right? So let's write that down. The basis here would be negative 3/5 of x cubed plus 2/5 of x squared plus x, comma, 2/5 of x cubed minus 3/5 of x squared plus 1. That's your basis. When I asked these problems on midterm 2, I basically just said if it is a subspace, find a basis, and I let people get away with just writing down the answer. This would be what you would write down. Now, if I ask you to convince me that it's a basis, so here's the answer, but what if I say I want you to convince me? Then we're going to go do what Coco was saying. We're going to double check, is it really Li, right? These are only two vectors, so we can just simply make sure they're not scalar multiples of each other. That's pretty obvious because there's a constant term here and there's no constant term here. So you're not going to be able to take something with a constant term and multiply it by a number and get another polynomial that does not have a constant term, right? So these are Li, and they are a spanning set by their very construction, right? The P of x, right? Anything of this form can be built out of these two. So these are a spanning set for S. Right? Also, another point to make here, guys, we didn't know ahead of time what the dimension of S was. Nobody, I mean, when you first saw the original problem, it says find a basis for S. I'm not sure if anybody knew how many vectors to expect. If we don't know the dimension ahead of time, then we can't really leverage that, you know, what's on that handout. I remember that handwritten recap from chapter 4 where I said, oh, well, if you know the dimension of the space and I give you a certain number of vectors, then you'll be able to tell me whether it's, you know, linearly independent, spanning set, both, and neither, all those kind of things, right? The problem with this example is we don't know anything about S. We've never seen it before until we did this example right now. Yeah? So we came up with two things here, but we didn't know that the dimension of S was 2 ahead of time. So we would still be having to justify, okay, I need to make sure these are Li and make sure that they're a spanning set. Once we've done that, then absolutely they are a basis and the dimension of S is 2. Okay. But it's a little different than when you know the dimension up front and then you're just asked a question. So like if I gave you these two polynomials and I said, are they a basis for P3 of R? What would you tell me? You would tell me no, because the dimension of P3 of R, you do know that number in advance, right? The dimension of P3 of R, what is it? It's 4, right? The dimension of P3 of R is 4, and I'm not giving you enough vectors here. They cannot possibly span P3 of R. They might be Li, but they definitely are not enough vectors to span, right? So this is the idea. We've got a vector space that takes $4,000 to span. We've spent $2,000 on these two vectors is not enough. Is not going to be able to span the whole space. Okay. Is this good? Kind of reviewing, getting some of this earlier stuff back into our mind a little bit. Okay. Let me see, what do I want to go with next? Let's do this one. Okay. This is also not from the review session official questions. Let's try this one. So here's another example. So consider the following system here. 9x1 plus 2x2 equals 1. Negative x1 plus 2x2 plus x3 equals negative 1. And 2x2 minus x3 equals negative 16. What I want to do is, if possible, find x2. So again, this is a little bit of an earlier topic. Let's see if we can do this. Okay. Anybody have any ideas? Okay. I'm sorry. Kramer's rule. Exactly. Exactly. We're solving a system of equations, and we're not looking for the whole solution. We're just looking for one of the terms, right? So you may remember that for any linear system of equations, it has to have a coefficient matrix that is square size, which this one does. It's 3 by 3. In fact, let me just note that here. We can make a matrix out of the coefficients: 9, 2, 0, negative 1, 2, 1, and 0, 2, negative 1, right? But there's a formula for the kth term of the solution. We put the determinant of A on the bottom, and then on the top. Do you guys remember this one?
Yeah.
This is why I'm reviewing this, because some of the things that maybe like it's been a while, I want to go back to. So on the top here, you're going to put the B2. And I'll just remind you that the B2 is the matrix that has, what you do is you take this matrix and you leave the first and third columns alone from the matrix A. But what you do, you put the right-hand side numbers into the B2 entry, so into the middle entry. So we have 1, negative 1, and negative 16. So that matrix goes on top, right? And then on the bottom, we have to put the determinant of the matrix A itself. So this is 9, 2, 0, negative 1, 2, 1, and 0, 2, negative 1, like that. So we have to divide these two numbers together. If the denominator comes out to 0, it's just going to mean there's no solution here, or the x2. It's not going to be possible. So you have to kind of watch out for that as well. So now, to do these determinants, if it's only a 3 by 3, you can get away with using the arrow method. But if you go back to midterm 1, and in fact the redo of midterm 1, I think also, I had both of these, I gave you a problem with a larger matrix, and I did that on purpose because I wanted to make sure you can do cofactor expansion. Actually, cofactor expansion becomes really the primary tool. If you're relying on the arrow method, then you're basically hoping that I'm only going to ask you a 3 by 3, right? Because if it's bigger than 3 by 3, we've got to be able to do the cofactor expansion. And you really, even for a 3 by 3, you need to know how to do the cofactor expansion just because of the chapter 7, 8, and 9 stuff, right? Because if you have a matrix where you're subtracting lambdas off of the main diagonal to try to solve for the eigenvalues, okay, so to change subjects for a minute, right? If you're trying to find the lambdas here, using the arrow method to do this is normally not going to be very easy because you don't have, you're going to get like a cubic equation that is going to be a mess to simplify. Whereas if, let's say I've made this matrix kind of nice and I've put some zeros in somewhere like that, if you know how to do cofactor expansion, you'll only need to take one term, which is the A33 minus lambda, and multiply it by the 2 by 2 determinant here, right? And that, a 2 by 2 leads to a quadratic, which is much easier to factor than a cubic. So make sure that you're able to do cofactor expansion because it's important even for 3 by 3 matrices later in the semester. And if the matrix is 4 by 4 or larger, you can't do the arrow method anyway. So it's just as good to kind of get used to it for now. Does anybody want me to review is everybody okay with cofactor expansion? Quick review of that might be good. So let's just do it maybe with this matrix on top here. Let's do it by cofactor expansion. I'm going to choose a row or a column of this matrix. I would like to choose a row or a column that has some zeros in it if I can. Right? Because every time there's a zero in a particular slot, I don't have to do the work for that slot. So does anybody want to suggest a row or a column to use on top here?
Third column?
Third column. Okay, let's do the third column right here. So what I'm going to get is, and let me remind you that there's an alternating pattern for the signs of the cofactors. So plus, minus, and so on throughout the whole matrix. So we're going to go plus, and then minus, and then plus. So we have a plus 0 from the first entry, times whatever the determinant is, but I don't care, because it's going to get multiplied by 0. Then we have a minus 1 times the determinant of the matrix that I get when I cross off the 2, 3 entry. So notice that the matrix that's left here, after I've crossed off the last column and the middle row, I've got these 4 numbers. 9 times negative 16, which I believe is negative 144, minus 0. This is just a little 2 by 2, right? So it should be negative 144. Okay? And then plus negative 1, which is this entry, times the 2 by 2 here. So negative 9 minus negative 1 is actually negative 8. So I'll put negative 8 right there. Does this make sense? You know, I'm going to give you tons of time on the test. If you really are questioning your numbers, let's say you try it with a particular row or column and you don't like the number looks kind of messy. You're like, Dr. Hammond probably wouldn't make the number that bad. Try a different row or column and see if you get the same answer. Because you should, no matter which row or column you use, you should get the same answer. If you were on a high pressure, time intensive test, you wouldn't be able to do that. But with plenty of time to sort of play with it, that shouldn't be too bad. So this is going to be on top. This is going to be what, 152? Right? And then I also have to do the bottom. Is this helping? Remember this now? On the bottom, let me just go across row 1 on the bottom. So I'll have 9 times the negative 2 minus 2, which is negative 4. And then minus 2 times negative 1 times negative 1, which is 1. So this is negative 36 minus 2 is negative 38. So this would be the answer. You don't really need to simplify that, but that's how you would do it. Okay? So the tricks for doing determinants, cofactor expansion is always a go-to. There's never a matrix where you can't use it. Another thing just to mention briefly is that let's say you want to do cofactor expansion, maybe it's a 4 by 4 matrix, but there's no zeros in it. What are you going to do? If I give you what if I ask you to find the determinant of, a 4 by 4? I give you this matrix right here. I don't think I've ever followed through on this threat yet, but there's always a first time for everything. I give you a 4 by 4 matrix with no zeros in it, and I say find the determinant. What are you going to do? Are you going to literally, first of all, you're not going to use an arrow method, right? Because there is no arrow method for a 4 by 4. Why shouldn't you be writing over there, darn it? It's okay, I'll come back over here. My camera is set up for these 2 boards. So you're not going to use the arrow method on a 4 by 4. So what are you going to do?
Reduce some rows and columns first.
Oh, okay, so one of our tools, exactly, one of our tools is we can do EROs and bring some zeros into the matrix. Now, unfortunately, okay, so great idea, Ivan, but let me throw cold water on that for a second. If I had, this matrix, and I said, gosh, okay, I don't have any zeros here. Using EROs here is very difficult because of the presence of the lambda in it, right? You know, you say, well, I'd like to get some more zeros in the matrix, so I'm going to multiply a multiple of this row times this row. Well, the problem is you're going to get these lambdas like, it's like they fuse throughout the whole matrix and it becomes really algebraically messy. So if you get something like this kind of a matrix, you probably are going to have a hint, right? Somebody's going to say, oh, well, here's what one or two of the lambdas are. Now figure out the rest of them. You can use the fun facts, right, to figure out the other eigenvalues, because this would be really tough. But if it was just this matrix, right, like that. Now here you could use the arrow method. So that's fine, but what if it was just this matrix? So if it was this matrix that I wrote on the other board over there, I would do exactly what Ivan suggested. I would do EROs. So this means I need everybody to be comfortable with how the EROs affect the determinant. So if you switch two rows of a matrix or two columns, you pick up a minus sign. There's a sign change. If you multiply a row through by a constant, the determinant will also multiply through by that same constant. And if you add a multiple of one row to another, there's no change. And actually, what I would probably do here is I would add multiples of the first row to all of the lower rows. And I would actually probably stop there. I would say, you know what, I've used my EROs a little bit. There's no change between this determinant and this one because I'm only using the Aij operation. And now I'm going to find the determinant of this one by milking that first column, right? And what you'll have is 1 times a little 3 by 3. Now you can use the arrow method. What a nice way for me to like test you guys on the whole chapter 3 in one question, right? We're not quite the whole chapter 3, but a lot of it, right? Because I'm checking if you understand how the EROs work, that you understand the tools for calculating determinants, the arrow method, and so on. Okay. So yeah, that's probably what I would do. The other thing that I'm a fan of doing with a 4x4 matrix, and that you did see on the first exam, is I might say, if this is the matrix capital A, I might ask you to find maybe not the whole inverse of the matrix, because that might be a bit much, but I might ask you to give me, let's say, the 4-1 entry of A inverse. Just find me one number of A inverse. So there's this adjoint method that is a nice formula for A inverse, and it goes way back again to chapter 3. A inverse is 1 over the determinant of the matrix times the adjoint of the matrix. And the adjoint of the matrix, let me write down one more step here. The adjoint of the matrix is the transpose of the matrix of cofactors. So if you transpose the matrix of cofactors, you'll get the adjoint. For a 4x4 matrix, there are 16 cofactors, right? Every single entry of the matrix has a corresponding cofactor, and that's probably more than I'm going to ask you to do. Why would I ask you to do 16 cofactors on the final exam? That seems like a really dumb question. I'd be much more likely to see if you know how to do one of them, right? That's what this question would be doing. It would basically be saying, well, the 4-1 entry of A inverse is going to be 1 over the determinant of A, all right, so you have to figure that out. And then times the 4-1 entry of the adjoint, which is actually the cofactor 1-4, right? Because remember that there's a transpose that happens right here. So you would be finding the 1-4 cofactor. So you just have to work that out. You have to find one cofactor. The 1-4 cofactor, how do you do that? Well, the 1-4 position is right here, right? So what we do is we find the determinant of the sub-matrix here. And let me not forget to remind you that this is a an odd position in the matrix, right? If you were to do the plus minus pattern, this is going to be a plus, minus, plus, and that's a minus. So after you find this determinant, which I don't know what it is, you have to put a minus on it, right? So in other words, I could also write it this way. 1 over the determinant of A times negative of M14. The minor, the 1,4 minor has to pick up a negative because it's in an odd position in the matrix. So just wanted to remind you about this A inverse approach here, right, that we have, and the fact that you can use it to pick off a specific entry. I've actually seen people take a 4x4 and do the Gauss-Jordan method, and the fractions are terrible. Actually, I was impressed on the first exam. I think I had one of these, and there were a couple people who actually did the whole thing with the Gauss-Jordan method and got it right. I was like, wow, good for you. That wasn't what I had in mind, but if it works, it works. So, okay. 625. Let me see what else I want to go over here. Oh, yeah, I should probably do some inner product stuff. Any questions on that? All right, so we reviewed Kramer's rule, the adjoint method. Okay, so Coco and George, I am going to do some stuff that you don't need to know for the test, and probably it's going to take the next time until we have to go. So if you guys don't want to stick around for now, that's fine. Again, tomorrow I'll have more time. And also, you can email me if you have questions. And I'm coming back tonight after they turn the power back on. But I just wanted you guys to know that. I'm going to do some chapter 5 stuff for the 250p crowd right now. Okay? It's up to you. I'm sure you have plenty to do. So yeah, let me just remind you guys real quick about some things from chapter 5, because it's been a while, a little bit of time. So let's do another example. Okay. I'm going to take V to be, this is also not from the review session questions. I'm finding lots of other good problems to do instead. Let's say we take C of 0, 1, and I'm going to define the inner product of f and g to be the integral from 0 to 1 of f of t squared times g of t dt. So remember this notation with the angle brackets. This is the inner product. So the question is this a valid inner product? Is it a valid inner product? So this is what we're going to try to figure out. Do we need to review the axioms? It's probably what we should do. That's actually why I wanted to bring this up. So before we actually answer the question, let me just mention the axioms again that we learned. Does anybody even remember how many there were?
4.
There's 4 of them, right? There's 4 axioms. I can call them A, B, C, and D. Do you remember that first axiom is a really important one?
I remember the one if we do if we do the inner product of f by itself, then it's going to be greater than 0.
That's right.
Unless
it's the 0 vector.
The 0 vector.
That's right. So the inner product of V with itself is always at least 0, and it's equal to 0 only if the vector V itself is in fact 0. Okay, so there's the first one. The second axiom, does anybody remember the next one?
CF, if you have the constant multiplied by, if you have a, I'm going to see.
You're doing the third one, but that's okay. I don't care what order they're
So
in.
the inner product of C times F and G, or yeah,
I'm going to use V and W just for my general
Sure.
notation, but yeah.
is equal to the inner product of C times W, or sorry, C times V and W.
That's right. So you can float a constant in and out of the inner product. That's exactly right. Does anybody know which one we skipped over here?
Yeah.
Which one is that?
VW equals WV.
Perfect. The inner product of V with W is equal to the inner product of W with V. Very good. Okay. And then finally, the last one is the one about addition. If I take V1 plus V2 and I take the inner product of that one with W, this is the same as the inner product of V1 with W plus the inner product of V2 with W, like that. Okay, so those are your axioms. If I give you a proposed inner product, the question is going to be, is it valid? I also want to remind you guys, if the vector space, this is not true for this example, but if the vector space is Rn and they don't give you an inner product, you should assume it's their usual dot product, right? The most natural of all inner products, the one that really motivates this whole chapter, right? So if they don't give you a formula, like here I gave you a formula, right? What if I didn't give you a formula? Well, that would be in the case of Rn, and in that case, you would assume, without further question, that it's the regular dot product that we're talking about, okay? So is this a valid inner product is a good question. I give you a proposal, and I ask you about it. So does anybody have any thoughts? We've got our axioms over there, and the question is, would they be true?
So we could try taking our F, the inner product of our F and our F.
Okay, so if we take the inner product, I think that's a great idea. The inner product of F with itself, right? Because that's along the lines of the first axiom.
And so if we're saying that ft is squared, then we would.
So this is just f of t times times g of t. But if g and f are the same, then this just becomes what? F of t 3 times, right? So the g is just another f, right? So it's just f of t times g of t. It's literally just like multiplying 3 things together here. Right? Now, is that going to always be greater than or equal to 0?
Not if it's negative. Not if it's a negative.
Not if it's a negative, exactly. So what we should do, if we're suspicious that this doesn't work, is give an example. So can somebody give me, an actual function, like something that you can think of from calculus? It doesn't have to be hard. That is negative.
-1.
-1. The constant function -1. Absolutely, right? You choose that function right there. Let's plug it into the integral, right? So then, under that assumption, the inner product of that function with itself is going to be the integral from 0 to 1 of -1 cubed dt. And of course, -1 cubed is just -1. So we're just pulling out a minus sign, and we get an answer of -1 out of that, right? Because you're going to integrate dt from 0 to 1 and get just t. Evaluated from 0 to 1 is just 1. So we have -1, which is not greater than 0. So axiom A fails. So that axiom fails, right? Actually, some of you might have noticed that the second axiom, normally the first axiom is the one to look at, so I'm glad that you guys sort of steered us in that direction. But the second axiom actually doesn't work either, because if you replace the fg with gf, see the second axiom? Switch the order of the two expressions. Well, if you switch the f and the g, if you switch them here, you could get a different integral, right? Because the first function is squared and the second one is not. So again, you could give an example. You could, choose a particular function for f, choose a different function for g, and show that that axiom fails. Okay, so these are the inner product axioms. That's what we're talking about right here. Let me give you another one. Now, by the way, if we have something that is a valid inner product, yeah, sorry, go ahead.
Is it required that the inner product of the zero vector with itself, does that have to become zero?
It does.
Okay.
Yeah. So, getting back to what I was saying, if we have something that is a valid inner product, you should be expecting a part B. Once we have a valid inner product, I'm probably going to do something else with that. So let me give you an example of that. Over here, so another example. Let's take V to be C of 0, 1. And I'm going to define the inner product of f and g to be equal to, again, I'm going to use an integral from 0 to 1 of t times f of t times g of t times dt. Okay, and I'm going to ask again, is this a valid inner product? Okay. Well, if you look at that first axiom again, I'm going to do this somewhat quickly because I think we have like 10 minutes left and then we probably should get out of here before we end up in the total darkness. You know, if you look at that first axiom here, f with f, what you're going to have here is an integral from 0 to 1 of t times f of t squared dt. And would you agree that that's always positive?
Yeah.
F of t squared is definitely positive. Now t can be negative, but not on this interval. Ooh, that looks like a great test question. If I put negative limits of integration, now it's not valid anymore, right?
Oh, Dr. Ann.
You don't like that, do you? That's just too nasty of me. You know what? My creative juices are not flowing anyway, so let's go back to what we had before. It's been one of those weeks. So okay, so we'll go back to 0 to 1. Yeah, so here you go. This would be definitely greater than or equal to 0. Okay, so and it's also pretty clear that the only way it would equal 0 is if the function inside the integrand was 0. Right. So you might mention that equals 0 only if f is 0. Just a very brief little, just write enough that I can see that you paid attention to it, like that you remembered the axiom. That's all you have to do. Okay, the rest of the axioms, if I switch the f and the g, well, inside the integral, if I switch the f and the g, am I going to get a different answer? No. So that's going to work, right? If I have a constant in front of the first function, right, a c inside of here, what can I do with that?
Pull it out.
Pull it out, right? That's exactly right. You want to factor a constant out of an integral. That's basically the third axiom, right? And so on and so forth. So all of these axioms work. I'm just going to say yes without doing all the details right now. Okay, because I want to get to my little follow-up question. My follow-up question then is, fine, so this is follow-up. We'll at least start in on the follow-up, and I may not get fully through it, but the follow-up is find an orthogonal basis for the span of 1x and x squared. Okay. By the way, guys, I want to mention also that I'm obviously not getting through all the problems I wanted to tonight because of the shortage of time we have. If anybody's thinking of coming again tomorrow, I'm gonna do these problems last. Because I know some of you may want to come back and see some more. So I will be starting tomorrow with different stuff so that you're not, I feel bad enough that you have to come twice if you want to see everything. But I won't be repeating this first and then making you wait 2 more hours to see anything new. I'll start with some new stuff, and then at the end I'll let you guys know, okay, now the rest of the problems are going to be what I did yesterday or whatever. So that you can kind of keep that straight. Okay, so when you see a problem like this, what comes into your mind immediately? Orthogonal, but that's in the question. But in terms of like how to do it, which is called
Gram-Schmidt.
the Gram-Schmidt process from section 5.3. That's it. 5.3, the Gram-Schmidt process. There we go. Okay. So I'm going to give you those formulas on the test for the Gram-Schmidt process. So the way the formulas work is that, you know, you have formulas for the new vectors. These are W's. Don't confuse these W's with the W's from section 9.5 that we just learned recently when you're doing a defective matrix. You know, the trouble with that is there's like all these different cases and different scenarios of it. You know what I mean? Depending on whether it's mixed eigenvalue or whether it's
just that basic, you know, like, you know how there's the difference from if we go to 2 over to where we need the 3.
Yeah, I mean
just
that's
so
a
we
big
don't
difference.
get the parts confused. You know how we have to do you know how it.
There's only one case where you have this super defective scenario where you have W3, W4, W5. The other cases are all the same. It's all just the same thing. It's just well, W2 is usually what it's called. So you have basically e to the lambda, I'm sorry, not W2, it's x2, which is e to the lambda t times W1 plus t times W2. Is this what you're talking about?
Yeah, and then the other one that goes for the third vector.
Yeah, that's in the case of a super defective.
Right, that's what I'm asking is if you'll put those on there, because otherwise sometimes I forget to do the t squared 1/2 if we have to go to the third one. You know?
I want you to know this. If you were to forget like the 2 on the bottom or something like that, I wouldn't, you know, care that much. But I do want you to understand how to create these solutions. So it should be pretty fresh.
Right, so no.
Right. Right. I do want you to know this. Oh, hi there. You haven't heard the great news.
What?
We're gonna stop in about 3 minutes.
Oh.
So you're right on time. Actually, could you not sit right there because I've got a camera behind you there. So the issue is, Oscar, is that they're going to turn the power off in the building.
Oh.
I did not find this out until yesterday, and basically I started at 5, and I said, well, we're going to go until 6:45, and then I'm going to be back here again tomorrow, but I'm not going to stay much longer because there is going to be pitch dark in this room in just a few minutes. So just so you know.
Yeah.
You can take a quick snapshot of what's on the board. I'm going to do all of this again tomorrow. And I'll have more time tomorrow because I won't be worrying about the blackout. But that's for right now, that's what we've got to deal with. Okay, so guys, real quick, I'm going to give you the Gram-Schmidt equations. W1 is just V1, right? W2 is just V2 minus, again, you don't need to memorize this because I'm going to give it to you, the inner product of V2 with W1 divided by the norm of W1 squared times W1. And then there's a similar formula down here, which I'm just going to write dot, dot, dot for right now. And those W's, they are your orthogonal basis, right? They are actually what we're hoping to come up with here. It says find an orthogonal basis. So what you want to do is just label these, right? You just want to label these as V1, V2, and V3. Okay? So then W1 is easy because it's just equal to V1, which would just be 1. And then for W2, let's see, how do we do this? We do V2, which was X, minus, I always just make myself a fraction here, some fraction times W1, and W1 is just 1. So in the numerator here, we have to take the inner product of V2 with W1. This is V2, it's just X, and W1 is just 1. I'm just going to use this formula. Here's my inner product formula that I was given. I'm just going to use that formula. So it's going to be an integral from 0 to 1 of t times V2, which is x. But see, the x should be changed to a t. Sorry, because it's a dummy variable of integration. You should not have x's and t's mixed together inside there. And then times 1 times dt, right? And then on the bottom, we have the norm squared. Okay, let me remind you guys. The norm of a vector is the square root of the inner product of that vector with itself. So if you square both sides of that, you just get the inner product of the vector with itself without the square root. Okay? So that's what I have on the denominator here. I'm going to have an integral from 0 to 1 of t times W1 twice, right? Which is 1 times 1. So 1 times 1 dt. So what is that? That's x minus, this is just the integral of t squared. From 0 to 1, it's just 1/3. And then on the bottom, when I integrate t from 0 to 1, I just get 1/2. So the answer is x minus 2/3. If I just do the fractions on that, that's what I should have for the second vector. Right. So far, so good. And then for the W3, this is just going to be V3. So the general formula is V3 minus the inner product of V3 with W1 over the norm of W1 squared times W1. And then another term, this is the nasty one. You have 3 terms here. The inner product of V3 with W2 divided by the norm of W2 squared times W2. I don't think in the history of me ever teaching this class I've ever done more than 3 vectors, so this would be the worst it could ever be. And now you just have to calculate all these terms. Okay. And you're just using this formula to do it, and you're just putting the right things in the right places. I guess I'll tell you what the answer comes out to be, but maybe I won't work it all out. It's not that interesting. It's going to be x squared, obviously, is the third vector there, minus, I'll just give you all the numbers. How about that? We have 1/4 over 1/2, right, times 1, and then minus 1/30 over 1/36 of the quantity x minus 2/3. So you see this is the W2 and the W1 here, right? All these numbers that are calculated, you're just doing the integration to figure those out. You just have to do the integration to figure those out. So does this make some sense? And you wouldn't even need to simplify that. Like, I would be okay with you just leaving it like that. You've done the bulk of the work. The main thing I wanted to see is, do you know how to work with inner product spaces? And that's pretty much giving it to me. Okay, does that kind of make sense? So I won't bother to write that one all the way out. Do you know how to find the angle between 2 vectors in an inner product space?
Cosine equals the inner product.
So there's a cosine of theta in there, right? And that's where the angle comes from. And it has the magnitude of V and the magnitude of W times the cosine of theta. So I think I had one of those on the exam, right? And it said find the angle between these 2 vectors, and it could be, you know, whatever the vector space is. Here it might be polynomials. So I would ask you, okay, find, well, it doesn't even have to be polynomials. Find the angle between, you know, sine of x and cosine of x. Something like that. So then you'd have to use this formula here, figure out the inner product of sine of x and cosine of x. Figure out the magnitude of sine of x, figure out the magnitude of the cosine of x, and solve for theta. So this is just another thing from this chapter. Also, Sorry, I'm pushing my luck, aren't I? I'm gonna turn the lights out. Any second it's gonna be like pitch black in here. Do you remember those problems where I said things like, suppose that UVW is an orthogonal set or something? I did this on the second midterm as well as the second midterm redo. And then I said things like, suppose that the magnitude of U is 1, and the magnitude of V is 5, and the magnitude of W is 7. And then I said, okay, why don't you try and figure out what's the inner product of U minus 3V plus 4W with V plus 5W or something like that. You remember so this kind of a little question? Just to remind you, this is really testing you on whether you know the inner product axioms, which I don't really get to test when I'm asking you a Graham-Schmidt question. So this is a likely question because it allows me to sort of, on sort of a fairly clean and simple basis, create a question where you have to use the axioms. What you basically do here, guys, literally, is you FOIL this out. You FOIL out the inner product into a bunch of terms. You're using those axioms when you do that, right? You're going to pull the constants out in front. Right? Does everybody understand? Let me press my luck. We only need 5 minutes to get outside, don't we?
Yeah.
Before they shut things down on it. Right, so like if I wanted to write this out, right, it would be what? The inner product of U with V, right? Plus 5 times the inner product of U with W. Oh, but I was told that my set is orthogonal, so there is no inner product between two different vectors, right? Remember, two vectors are perpendicular if their inner product is 0. So that term would be gone. So I have U with, oh, and so is this one. Yeah, sorry, they're both gone. Okay. Then we would have minus 3 times the inner product of V with itself, right? And then we would have minus 15, 3 and 5, right? 15 times the inner product of V and W, but that's 0. And then 4 times the inner product of W with V, but that's 0. And then finally 4 times 5, which is 20 times the inner product of W with itself,
which is 7.
So we have, right, so we have negative 3 times the norm of V, sorry, the inner product of V with itself, which is what?
5.
It's not 5.
Square root of 5. No.
Let's be careful. This number here is, so the inner product of V with itself is the norm of V squared, right? So we actually have to put a 25 there, right? The inner product of a vector with itself is the square of the norm, right? And then finally we have plus 20 times, what am I going to put for the inner product of W with itself? 49, exactly. So this would be 49 times 20 minus 3 times 25. Guys, if you get this and you don't want to simplify it, I'm fine with that. I'm the ultimate, professor of being okay with unsimplified answers. And so many times people do the simplification, which isn't even the 250B part, and then somehow they get it all fumbled up. And I'd rather just have you leave it in good shape in the way that it is here. So, okay, so I didn't really do any review of the midterm 3 stuff today because we just did that a week ago. What else have we not gotten around to talking about? There's a lot of things I could talk more about. Row space, null space, column space of a matrix. There's the linear independence. How do you check that kind of thing? There is, well, of course, chapter 2 is mostly just EROs and stuff. You might look at the invertible matrix theorem because it's got a good summary of the theoretical stuff about linear systems that are square in size. And then linear transformations, didn't really do much on that. Kernel and range, that could have been better on the third test. That could have been much better for a lot of you. So make sure you review kernel and range again. Make sure that for your kernel, your vectors look like vectors from V. Whether it's polynomials or matrices or whatever, they should not look like just slots. If it's supposed to be the kernel, it should look like whatever the vectors of V look like. W is the range, right? W is what the range is part of. So whatever the vectors of W look like, that's what your answer for the range should look like. Whether it's a basis or a spanning set or whatever it is I'm asking about the range, make sure your answer is reasonable, right? So it should look like vectors from the right space. I give partial credit for that kind of stuff, but then I also, if I see an answer that makes no sense, like if I say what color is the sky, and you say it's green,
Orthogonal.
you know, or, yeah, if you say the sky is green, I can say, well, they understand the question, and you know, they have an idea what's going on, right? It didn't get the right answer, but they have an idea what's going on. But if I say what color is the sky, and you say, you know, table, or something like that, then I'm like, I don't know how to help you at that point. So make sure you're giving answers that are really reasonable to the questions. All right, let's get out of here before they power us down. I'll be back tomorrow at 3 in this same room. I'll do different problems first. I'm also going to come back to my office tonight when they turn the power back on at 9 p.m. So I'm going to take 2 hours to get out of here, but I'll be back at about 9 o'clock and do some more stuff. So thanks for hanging in there with me, guys. We'll see you again soon, I'm sure. I've got to turn this thing off, too.